Hello ladies and gentlemen, Mr. Grouproad here. This time around, let's figure out what current is. So we should have an understanding what electricity is. We should have a general idea what voltage is, which that's kind of a more tricky one to understand. So this time around, let's figure out what current actually is. And then after this one, we'll figure out what resistance is. So current and resistance, I think that's something that in general, we tend to find to be a little bit more easy to understand. So the questions in blue here, we're going to focus in on this lesson. So what actually is current? What are analogies of what current is like? And then you'll get to create one of your own. What affects current in an electrical circuit? So what could increase current, what could decrease it, and so on. These black questions, we'll get to those in a different lesson. So let's move on. So what actually is current? So if we look at the actual scientific definition, it's kind of a mouthful here. Let's take a look at it though. So it says, so first of all, amp is how we measure current. An ampere, so current in electrical circuit, is equivalent to 1 coulomb per second. So amps or current is used to express the flow rate of electric charge. Now this number here, 6.241 times 10 to the 18th, some scientific notation. What that means is 1 amp is this number here. So in 1 second, for 1 amp, this is how many electrons are passing through a section within a second. Now, this is kind of a big number, kind of hard to picture. It's just crazy huge. So what I want you to imagine is like the electrons are particles and they're passing through a wire. And in 1 second, with 1 amp, that's how many pass through that wire. We're going to get a little bit more into this, try and help you understand a little bit better. But the main thing I want you to understand right now is what's current or what are amps. It's basically the flow rate of electric charge. So let's take a look at some examples. Let's look at some analogies and try and help us to understand this a little bit better. What I'd like you to think about is a bucket. Imagine that bucket has sand in it. So we can do analogies with electricity with water, and that can usually work very nicely. But one thing with water is it's a liquid, so we don't really see the particles with our eyes. The particles are the atoms, molecules, they're in there in the water, but we can't see those with our eye. So let's say sand. So instead of water, so imagine this here would be tan. So imagine this is full of sand, just like this plastic one is here. So now these sand particles we can see. What I want you to imagine is those sand particles then represent the electron. The bucket could say be a battery, and then the holes maybe how thick the wire is or something like that. So inside the bucket, imagine both buckets have the same amount of sand. We put a hole in that bucket. Let's just say bucket number 1. Here's bucket number 1. We put a hole in that bucket. Let's say it's the size of your pinky. So look at your pinky and imagine we drilled a hole in that bucket the size of your pinky, and now that sand is pouring out. What current would be is, let's say we have a stopwatch, and then as soon as that sand comes pouring out, we click start, and then a second later, stop. So we're watching that sand come out, and let's say we collected how much came out in 1 second, and then we count those particles. Remember, those particles would be representing the electrons in an electric circuit. So then what we would do is we would count those particles, and then that would be the current. That would be, the current would be, for this situation, for bucket number 1, how many particles are coming out in 1 second. Let's just say there's 1,000. So with bucket number 1, it has a hole the size of your pinky, and in 1 second, 1,000 little sand particles came out of there. Now, imagine bucket number 2. This time in bucket number 2, let's say we put a hole the size of your thumb. So we drill a hole in there the size of your thumb, same amount of sand, same kind of sand in the bucket. So on that bucket, we got our stopwatch, start it, watching the sand come out, stop it 1 second later. And remember this time, so this bucket has a hole the size of your thumb, and we collected the sand that came out within that second. Now, what bucket had a higher current, do you think? Bucket number 1 or bucket number 2? Bucket 2 had a higher current, and the way that we know that is more particles flowed out of the bucket. And we know that because we could actually count them. We could physically count all those different sand grains from bucket number 2, compare that to bucket number 1. And let's say bucket number 2 let out, let's say 10,000 sand particles, and bucket number 1 was only 1,000 sand particles. So we can do that with an electrical circuit. We're not going to count the electrons by like with our eyes or something. We have a multimeter that we can stick on there to do that. So we have tools that we use to do that. Here's another example, this time using water. If you look at this here and this here, these two are the same. It's trying to represent voltage, so the pressure of the water, so remember we talked about pressure for voltage. This water is pressing down, so this water up here is pressing down on this water down here. Same thing with this one. And same thing with this one. The water up here is pressing down on here. But if you notice, what's the difference between these two setups? So I'm sure you noticed that if we call this like a pipe, this pipe is a smaller diameter than this pipe. So what's going to happen, this is just like our bucket example, this one has a bigger hole, so that water is going to come out faster. There's going to be more water coming out. So we're going to have higher current versus this one here. And there's ways that we can reduce that current. So like we said, like the diameter of the hole, that's one way we can reduce current. Same thing like in an electrical circuit, we can reduce current by having like a smaller gauge wire, like a thinner wire. That's one way we can do it. So for example, that would be resistance. So this one is flowing nice and easily, but this pipe is kind of squished, so it requires more force to push it through. Now, another thing I want you to think about would be pressure, how pressure affects the current. So if we think of our balloon examples, there's not much pressure here, medium pressure, higher pressure, because we got the fire, then we get the animal sitting on top of the balloon. There's higher pressure. These atoms inside of here, they want to get out like harder, like more, like get me out of here than this balloon. This balloon, they definitely want to get out, but not as bad as this one. So between these two balloons, which one, let's say we untie the knot and we let the air out, which one is going to get rid of the air faster? Which of these two balloons is going to have a higher current? So what matters is that you tried and that you answered. This one would have a higher current. The reason why, there's more pressure. It has a higher voltage. It's trying to push that air out harder. Thus, more air particles are going to come out and come out faster. Let's check out an animation now of what current looks like. The blue are going to represent the electrons. This would be a wire. The red would represent the positive charges. So if we push play here, the electrons are flowing through that wire. And then again, in the amount of time, we could count how many electrons made it through. And here's what current looks like within a circuit. These would be light bulbs, and then there's switches. But we can see the electrons flowing through the wires. Thanks for checking this lesson out. Stay tuned for more information about current.